here's what's going on. We're going to do problem number 1. Perfect. Number 1A, and the problem is consider the titration of titration. Left out the molarity. Oh, that is 100 mils acetic acid. That is 2.0 mol. And for part A, I'm asking you, A, what is what we're going to do is we're going to track this titration by following the pH over the course of the entire thing. So part A, we got to find the pH before we start. And this is fairly straightforward. The notation here, I'm going to use HOAC on the test. Yeah, that's what I used. And so we have to write the equilibrium out. What goes on the right-hand side?
Hydronium.
Sorry?
Hydronium and
H3O.
the conjugate.
What do we call that conjugate base? What do we call this ion?
That's it's acetic acid.
It's the
It's
acetic
acetate.
Acetate, yes. So yeah, I just want to, because somebody was asking earlier about that, do we need to know what the acids and the conjugate bases are? And yeah, the answer is yes. That's part of the thing we have to understand. And even though this was written at the top of the question, I do want you to know that this is the parent acid, acetic acid. You can go even though this is acetic acid, the conjugate base of the acetic acid is the acetate ion. And actually, it would be if this is incomplete. This is just the anion. What's the spectator ion?
The water.
The titration is going to be, well, in this case, the spectator.
Oh, the spectator.
In this case, it's the hydronium ion and the acetate ion. This is from the parent equilibrium of just acetic acid and water. So as we do the titration, it's going to be sodium acetate because we're using sodium hydroxide. And the the hydroxide is going to combine with a proton to make water. We're going to make sodium acetate. We draw out the equilibrium, and you have to do that on the test. Write the equilibrium, even though it's written up above, you have to write this out. And what are we going to do?
Ice chart.
We're going to hit the ice. And what is, before we start, what do we have to check?
If it's
That our assumption's gonna be our approximation.
That our approximation is going to be valid. And what's the criteria for that? It's going to be
If it's
greater than
over
100.
100, then it's less than 5%.
Yeah, if what's over 100?
The number that we get.
The
The
ratio
number-
of
The
the
ratio of
molarity
the
over
concentrations.
the...
Yeah, the molarity divided by the Ka. If it's greater than 100, then our approximation is going to be valid. And by what makes an approximation valid?
If the it's less than your error from your instruments.
Yeah, if the error is going to be beyond the certainty of our measurement.
You said it was its polarity over the pKa?
No, over Ka.
Over Ka.
And the criteria for whether an approximation is reasonable or not has to do with when you're going to go into the lab and actually observe this. Our pH meters aren't that sensitive, and so the certainty there is going to be a limiting factor. And if it gives you an error that is less than the certainty of the instrument, then it's a reasonable approximation. This means it's not going to be observable. On most routine instruments, there are more sophisticated, delicate experiments, but we're not usually going to be going to the rate of a length. So the approximation we have to check out is that 2.0 molar and 2.0 divided by the Ka, and the Ka is what?
1.8 times 10 to the fifth, negative fifth.
Yeah, but it would be a more convenient way of expressing it. Ka is
10 to the negative 4.7?
Yeah, 10 to the negative pKa. So 10 to the negative 4.75. And that's going to be equal, let's rewrite 2. What's 2?
10 to the 0.301.
301 divided by 10 to the minus 4.75. And now, what other rules will exponents have me do?
Subtract.
I subtract. And so it's 4.75. This is on my scratch paper, 0.301. And that's going to be a 9, that's going to be a 4, and this is going to be a 4. That's 4.449. So this is equal to 10 to the 4.449, which, ballpark, what is that?
Did you go the wrong way on that?
No.
Yeah, you subtracted that.
You're gonna subtract the negative?
Because you said
Well, if I subtract
Subtract the
it, but when I
negative side.
subtract a minus, I add.
Yeah.
So you'd be at
And you subtract.
5051.
Oh, 0.301. Oh, yeah, you're right. I would add it. It'd be even greater.
Yeah.
5.7.
Thank you.
It's
Good
closer
point.
to 100,000.
It's closer to 100,000 than it is. I was going to say it was about 449. That's about close to 3. This would be about 30,000, but in fact, you're right. I did that the wrong way. Thanks, James. Yeah, it's 301. I subtracted when I should have added. 1, 5, 7, and 3 is 10. 5, so that's 100,000. Yeah, which is bigger than 100. So, not wrong. Much greater than 100. And therefore, the approximation is valid. So we have to check that. Even though I've told you right up front, we're going to have a weak acid equilibrium and this approximation is going to work, you have to verify that in order to make sure you're checking. In other words, verify that you don't trust me, because you're not supposed to. Don't take anything I tell you on faith. Keep me honest. Okay? And so, get back to the ice. What's this?
Never mind.
Well, no.
2,
0.2 or 2, sorry.
0, 0,
What's this?
minus x. Plus x.
Plus x?
Plus x.
Plus x. And at equilibrium, we have 2 minus x, x, and x. And so, we should probably go over this board. And so that means that Ka, which is equal to 10 minus 4.75, is equal to x squared over 2 minus x. And now our approximation is what?
X squared over 2.
Well, in other words, what is the approximation?
Square root of 2.
I can ignore the x term in the denominator. Okay. The squiggly line, x squared over 2, and that means that 2 times 10 to the minus 4.75 is equal to x squared. And so now I just rewrite this. What's 2?
10 to the
10 to
.301.
Equals x squared, and now I just have to add this together, which we have already done over there,
Yeah.
which is 5.051 equals 10 to the 5.
This time you're subtracting.
It'll be 4 point.
Oh, no,
Yeah,
I'm
that'll be-
subtracting.
That'll be the 4.449.
It's the 4.49 that I got, yeah.
Negative.
Negative 4.49, thank you. Yeah, the rules of exponents, okay. And
It's
so-
449.
Or for what? 449?
449.
Okay. Okay. So this is what we come up with, and now therefore x is equal to 10 minus 4.449. Square root of that, 1/2 power. What do the rules of exponents have me do? Divide by 2. Okay, so on my scratch paper, I go 2 goes into 4.449, 2.2245. It's way beyond our ability to detect that far, and I wouldn't believe any pH meter that far to the right of a decimal. And so this is going to be,
Next line down.
next line down, equals 10 to the minus 2.2245. That's going to be equal to 10 to the minus 2.22. And I believe that to the right of the decimal is sort of credible. This is what is significant and what isn't here. How many sig figs are this?
It's 2. 3.
Yeah, this is 2 sig figs. And if we look at the original question, I had 2 sig figs in the malaria.
Right, okay.
So that would be a reasonable, we're not stretching it at all. And that's equal to the hydronium ion concentration. Right. And therefore, is equal to what?
2.22.
Yeah, negative log of
Negative.
10 to the minus 2.22 equals 2.22. Okay. And that's problem A. Is there any questions? Wait, you have a question? Okay. No questions? Okay.
Good. Part 2.
That's a wrap.